now an associate professor in the department, doing research mainly in the large area of communication. And he has a couple of NSF awards, including prestigious NSF Career Award, which he got recently. Yeah. Welcome.
Right. Thank you, Sumi. Thank you for coming here. So, Friday afternoon.
Yeah.
So today talk, I will talk about large scale approximate inference. So it's a topic from statistics and from machine learning, and talk about the theory, the algorithms, and the applications. And I would like to acknowledge the support from NSF. And for this grants, I'm looking forward to recruit a few PhD students for the next year. And if you see this talk interesting, or if you know some friends who want to do a PhD with me, please come up and talk to me. So I have the fund to fully support the PhD student, 3 of them. All right. So also, I just from my personal side, I just want to acknowledge my former master advisor from University of Saskatchewan, and he passed away last month at the age of 49, very young. He got a stroke. Oh, yes. So I owe him a lot because I started to do research. He's the first person who introduced me to research, guided me everything in terms of research methodologies, writing papers, a lot of things. And yeah, he was 49. All right, so let's start with the first section. We'll talk about the approximate inference with AMP, and this is a very interesting topic. I'm still working on it. And I think that the best way that I learn from the topic is I give the presentation of that. So I can go quickly and wrap the idea together and put it up in an organized way and give the talk. If I don't understand, that's fine, right? So we require the understanding. All right, so let's talk about the first example, like one example from, you can use AMP. Everybody knows about linear regression. So linear regression is first topic in machine learning you can learn. So in linear regression, you want to learn some way vector X, right? And from the observed data Y. So A here is just the data, right? The features all you have now. Y is your observation. Maybe from your learning, you see the notation a little bit different. You might see that people write Y equal to X times W. W is the way vector, right? I just use AX, right? So comment, we model it, we put some noise factor inside, and A here is the matrix that might present collected feature data or just the physical measurement process. So, and here just the noise, is the perturbation or the modeling error. And what you want here is that you try to give the best weight estimation from the observed data and from your data set. And here just, some data, just the ratio system. By the way, my talk is a lot of math. Coming up is tons of math. And I put all together because it could be a good reference for me later on. Something put together. If you want some slides like this, I can send to you. Just shoot me the email. I will send the slide to you. All right. So how you try to estimate the weight, right? So a popular approach to recover X is you use optimization problems. So we introduce residual cost loss, right? Y equal to AX squared. And then we also introduce the regularizer, G of X. And then we have some lambda is the trade-off, right? So there's some special cases here. So one case is if you don't look at the the regularizer, right? Just look at the residual loss alone, and you try to find out what should be X. And this minimization problem, we know there's a closed form solution for this. If you had overdetermined system, meaning that you have m bigger than n, and m here is the number of observation, and here is the number of feature. Right? So in that case, you overdetermined system, the closed form solution is just the Penrose pseudo inverse, right? More Penrose pseudo inverse. So this is well known. Maybe that you don't like this matrix inverse, and there's an algorithm for stochastic optimization allowing you to try to optimize X using gradient descent. You don't want to perform this version. For underdetermined system, when you have m smaller than n, which means you have less number of observations than the number of unknown features, weight factors. In that case, for full rank A, you try to perform the optimization problem, but you try to find the weight vector that has the minimum norm. Right? Because in an underdetermined system, you have many solutions. You have infinite number of solutions. This is basic stuff from linear algebra. Okay, you have the linear set of equations, ax equal to y, comes up solution where you try to find the one that has the minimum norm. You take the norm 2, and again, this is we have the left side pseudo inverse solution, closed form. Okay, so the other method is you want to try to make it the problem is more stable and then less overfitting. Is that you introduce some regularizer, so you can impose g of x is just the norm of x square over 2. So in that case, we got the rich regression, right? So the next topic in machine learning is people would say, okay, rich regression. So rich regression, again, you can also have closed form solution, just 8. You introduce the regularizer inside. You look at so again, if you don't want to do matrix inversion, you can use stochastic gradient descent to find the solution, right? Slowly refine the solution. As more data you have, and you keep updating, and you get the better estimation for the weight factor. The other method, very popular, is the lasso regression. It's the next step. So we introduced the norm 1, not norm 2. Okay, the L1 norm. And the L1 norm is just the summation of the absolute value. Okay, just I forgot to put it in, but okay. Okay. You had a marker I can borrow, but all right. So the lasso problem is that we introduced the norm 1, and I think this was the research like 30 years ago. People were coming up with the norm 1, and somehow, great. Our solution for x had a lot of 0. We call it the sparsity in the solution of x. We want that because when you have a lot of 0 in the weight vector x, you can reduce the number of features in your data set. Guys, next time you don't need to store 50, 1,000 features for one sample. You might just store 10 of them, 5 of them, or 10 of them, just the most significant features alone. One way, you use the lasso regression, or you use BCA, principal component analysis. So those are popular methods for you to do feature selection. Lasso is still very popular. It's the most popular method for sparsity, or for signal recovery with sparsity. So in my talk here, I look at the simple case here for we call the separable regularizer, in the sense that we impose the function g of x individually, independently for each component in x. Right? So we put it in, we impose it individually for each xi, gi, not gk. All right. So that is the introduction. Some of the things you might see in your first course in machine learning. All right, so if you want to solve, let's say the optimization problem at the beginning we talk, right, this optimization problem, what are the ways we can go? So it depends. It depends on if the function g of x, the convex function, is smooth or is non-smooth. So some function of g of x are smooth, like the norm 2 is the parabolica, which is smooth. The norm 1 is not smooth because the norm 1 is have the discontinuity at 0. The norm 1 is the absolute value, so it's non-smooth at 0. Right? So we have to look at the way that we try to solve this optimization problem. One of the most popular method was the E star algorithm, the iterative shrinkage threshold algorithm, and I think that was developed like 30 years ago, I think. So the way it goes is that we look at the optimization problem, we do gradient descent to the smooth part of the cost function. So you have y equal to ax squared, which is a smooth thing. You can take the gradient of it, which is a transpose multiplied with y subtract a of x. So that is the smooth one. So you go to gradient descent for the smooth part, and then you perform we call the proximal operator on the non-smooth g of x. So you go optimize for one function, find the solution, and then optimize with respect to the g of x with the other function. All right, and there's many methods for you to derive E star and then prove its convergence. It is a really nice algorithm, and that's improvement like phi star pass E star, which can improve the convergence. But you can apply E star into the lasso regression problem. So by the way, the lasso problem is convex. It's just not smooth. Right? And then there's a package out there. You just call lasso regression. They solve for you. But really, what is behind the scene? What's the algorithm that helps you to optimize something that is not smooth? So we, in terms of E star, the idea is we, as I say, we do gradient descent. So alpha is just a step size for your gradient descent. This is a step size. This is the gradient. All right. So then you perform the proximal operator. Now this one is you can do it for each element of the vector x. Before, if you look at the original problem, there's some coupling right here. I have actually coupling everything of x here. You cannot just optimize individual element of x. Right? However, once you do the gradient descent, you have z. Now you can do the proximal operator individually for x. So when you have z, you can find the max xi. This problem is now you can have a closed form solution. Okay, and this we call the sort thresholding algorithm. All right, so basically, what I mean, this one it has a closed form solution in the sense. So if zi here is too small, we force it to be 0. If it's big, then we just subtract this amount alpha lambda. So if you plot this type of function, this operator, it looks like this. So the beauty of lasso, why it gives you sparsity. A lot of 0 solution is because anything falling into this region will become 0. So which means that feature will not be counted. I mean, it's extremely important. It has a lot of application, especially in biology. I mean, and a lot of the big data. They want to know which are the features that are important to doing the regression. So you can shrink this threshold and then make it more sparsity or less sparsity. So if you put the threshold bigger, meaning that if you increase lambda, put the threshold larger, then a lot of them will be falling close to 0, will be forced to be 0. So that's the idea. All right, so if we start look at the problem entirely from optimization points of view, right? We had the cost function, performs the algorithm to minimize the cost function. Right? Now I look at the perspective from probability and statistics. So I look at from Bayesian interpretation of the regression problem for now. Right? So let's say the problem we want to solve is, sorry, if I had to go back again with this problem. The problem is that we want to find a solution for this optimization problem. So we will treat this problem is the first portion we call the likelihood function. The second portion we call the prior information of X. Okay. So this is because the map problem, the maximum posteriori probability mapped estimation of X under the prior B of X follow this type of exponential function, and we assume that the noise to be Gaussian. Okay. So if you look at the map problem, it just maximize B of Y given X multiplied with B of X. Right? So this and now it's jumping to probability or whatnot. Now if you take the log of this, right, it becomes the log of B Y of X, but this is Gaussian now. And if you take the log exponential, it's gone. Gaussian distribution. This is the BDF of the Gaussian distribution. Multivariable Gaussian distribution. Right? So if you remove that, you have this cost function. Now, log of B of X, if you remove this exponential, you have the regularizer factor. So the regression problem, no more or less, is a map problem, MAP problem. We can assume that typically we assume that the prior to be independent, so meaning that all the weight factors are independent. Right? So we can enforce once they have independent, the joint probability is just the product of the BDF of individual components. Right? For rich regression, we treat X to be Gaussian. If you have a BDF of the Gaussian, again, you just put this the norm tools. Here, take the log of it, you have lambda X squared. So that's the rich regression. So we have Gaussian prior. Last problem is the Laplacian prior. If you look at if we look at the BDF of the Laplacian distribution, it's like exponential distribution, but it has two both the negative part and the positive part. So the BDF of it is a known one of X. Okay? And you take the absolute value. Basically, this is Laplacian distribution. Right? So when you take the log, it just becomes the regularizer, known one. Some application, you might want to have X to be discrete. What happens if you don't want to have the weight factors like 1.2 something? If you want to implement in hardware, you want to be the discrete number, like 1, 2 something, so you can put the bits in the calculations easier for you to implement. Instead of you floating on something, you might want X to be discrete, maybe faster for hardware implementation. In that case, can we solve for X? And in general, it's not that easy. Right? If you want to force X to be discrete, in general, this problem becomes very complicated. It becomes exponentially complicated. We don't want that. So we want to have approximate solution. That's the key idea of this topic today, the talk today. All right. In practice, we might want to get the MSE, the minimum, the mean square error optimal solution. What's the difference? The math problem is that you try to maximize because the posterior distribution. Right? So if you have this and then you normalize this probability, we call the posterior distribution. The math is try to maximize the posterior distribution. The MMSE solution is you try to find the posterior mean. Right? The mode is the highest point of the BDF. The mean is the mean expectation of the BDF. Right? So we want to find the expectation of X given Y. Okay. So in that case, supposedly if you can derive the posterior distribution be X given Y, then Y is your data, your observation. X is your the thing that you want to estimate. If you can find out that PDF, you can do is the expectation. And that is the optimal solution. That's the best you can do because it gives you the minimum amount of error compared to the true value of X. All right. So exact MMSE estimate, MMSE estimation problem, or we call it the MMSE inference, is computational intractable. Most of the time, you cannot derive the B of X given Y. It's very simple. If you use Bayesian theorem, and Bx given Y is just By given X multiplied with B of X divided by B of Y. Everybody knows that, right? And that's a math, all right? So this we call the prior. Sorry, this we call the likelihood. This we call prior. This we call the data, the distribution of the data. General in it's very hard for you to evaluate the B of Y. So the difficulty is to obtain the model evidence, the B of Y. And if you have this B of Y, just the integration of Bxy with respect to X, then it's probability. If you take that expectation integration with X, it's just gone. So what you have that is the marginal distribution of Y. All right, so in general, MMSE is very hard to obtain, and it's only a few cases that you can write the solution in closed form. This, as far as I know, only the case when we have a Gaussian error and a Gaussian prior. Meaning that this is Gaussian, By given X is Gaussian, this is also Gaussian. Then the posterior distribution is also Gaussian in closed form. Right? But it's very nice. Anything related to Gaussian distribution is nice. All right, so in general, we cannot get B of X given Y. And basically, this is called the inference problem because what you observe is something you want to infer what's the distribution of X to something else. Right? Something that model your system. So actually something that model your system. You want to infer what you observe from data. You want to infer back what is originally about X. And from the perspective of Bayesian statistics, you can have some prior distribution for X. That's thing that you don't know anything from the data, the observation. We have some distribution for X, and once you have data observation, we see Y. You try to give the better estimation, better inference for X. All right, so we need approximate solution to the posterior PDF, Bx given Y. Now it's the thing. We use a factor graph representation of the problem. Let's say that we assume Gaussian noise. Right? So we want to obtain Bx given Y, and this probability we just technically call the proportional to the By given X have the distribution of X. Now By given X is a Gaussian distribution, okay? Because we assume to be Gaussian noise. And we had a prior distribution for X, right? You just take a course on statistical machine learning, and then probably you know something. There should be a few lectures to cover. We call the factor graph. That's no, right? So it's a method that allows you to calculate the distribution of the variable in the graph. So, Xi is a node. We want to know what should be the distribution of it, and we put in a factor graph. One side we have variable naught, which is X1 to Xn, and we had a factors, which is the distribution. So Xi, you can think of what all of them will be combined into Y1. This is Y1 is just the linear combination of AI, A1 from X, and then you have Y2 and so on. All right. Now, if we look at this graph and then we try to derive the distribution for X1, X2. So these are the theory they call Bayesian net, back to the AV. And I'm pretty sure if you open any statistical machine learning book, there should be a couple of chapters on Bayesian net and the message passing algorithm. So the way we try to do inference here, if you had a graph, the factor graph is you perform passing the message along the graph. It's just the belief, we call the belief propagation. So some node like this, very simple. So some node like this, make the belief that what should be the distribution for x1? What is the distribution for x2? And this pass the message to this node. And at the node, once you collect all information, all the messages coming up and tell me what it should be my distribution is. So once I have the message coming from all the nodes coming in, I combine with my prior information, I refine my the distribution again. Okay, so combining the message together. All right, so there are two types of inference algorithms. One is the sum product algorithm. Basically, we try to figure out what is the marginal posterior. So the probability of xi, we want to do the marginal distribution visually for xi, and that's allow you to have the MMSE estimation. Because once you have this distribution, you just can find the expectation of that easily. The other method is the sum maximum algorithm, and that's give you the map estimation. Okay. There's two methods that allow you to do the message passing, both of which you pass locally computed message. And by the way, message is just VDF, probability density function. Message is belief. Belief is just distribution. How you look like, where you should be in the value of x should be, which is the VDF, right? You pass the message along the graph, and when the graph contains no loop, this is kind of the tree structure. You had the root, and then you had the branch out, and then it looks like a tree. Both methods would use the exact estimate. This is the theory, and people already proved it. And so nothing new here. However, if you have the loopy graphs, so the graph would have some loop. It's not a tree structure. Something like this, we call it the loopy graph. But I can go from here to here and then get back and go back here to that. It's a loop in the graph. And for loopy graph, you don't have the exact solution. Okay? Because you can think of, if you have something wrong, some not exact solution, if we pass along, if we come back, it's still the inexact. If you have the tree structure, one of the node, you can estimate the exact distribution of the, you can pass along, it's no going back, it's going along, everything would be correct, go back into the root. Right, that's not the idea. But for the loopy graph, it's not. All right, so in any case, the computation needed for the exact sum product or the maximum product algorithm are still intractable in the high dimensional case. The reason is that's the theory. That's the theory in terms of the graph, in terms of message passing. But once you really sit down and do programming, and you have a big graph, it's a big is M is 1,000, N can be 1,000. Very big graph. You can have the tons of messages to pass around. Very complicated algorithm that can go for exponential complexity. So the algorithm is out there, but it can be intractable. And in terms of computational science, we don't want something like this. So let's go further in terms of the message passing. So basically, you pass the message between the variable and the factor nodes. Right? Variable nodes is x, factor nodes is y, and then you pass the information. And just a bit of mathematics. Basically, we denote the message from the factor node k into the variable I. That's k to I. It will tell you what the distribution of xi should be, and we also denote the message from I to k. So from variable I to the factor node k. Just tell y is now what I look like now. What is my distribution now? So that's the idea of message passing. You pass the information along the graph. All right, in terms of how to calculate the message, again, it's on the mark now. So once you, if you look at with respect to factor node k, right, you collect all the message from the node together, right? And if I want to tell what should be I look like, I would take the product of all the message from the neighbor, the one that connected k, but not I. You look at all the neighbor, but not related to I. And you don't want to you don't want to multiply with yourself. If something wrong, you don't want to remove it. That's the idea. All right, so we take a product, and then you have the VDF, the factor. This is Gaussian, and if you integration everything out, not related to I, you would have a message for example. Right, that's the theory of message passing. Now, once you head to the variable node, you collect all the message from all the factor nodes coming to you, tell you what you look like, and then you also have yourself the prior information at the outside. Then you refine. Now you can calculate and refine your the distribution and as out. And if you want to pass back to k, you have to ignore the message coming from k. So that's the theory, right? We want to make sure this is the valid VDF. This is also the valid VDF. Right? Of course, we don't want to do that. Very complicated. All right, so the idea is I want to illustrate to you again. So basically, we have one term, everything from the variable node. We pass the message to factor one, the first factor here, and the first factor would figure out the message blue curve, pass it back into all the variable nodes and tell each variable node the distribution. Right? The key idea of this AMP approximate message passing here is we use the central limit theorem. So if you look at the combination of, let's say, y of k something, right? So it's just the summation of because the vector product you have AX. Now you look at the k row for the matrix A. It's just a combination of different fj. You have that thing go, and this is by the way, this is Gaussian distribution. And use this notation, we just have this yk is the random variable. This is the mean, and this is the variable. And then you have the message coming from all the nodes. Coming, right? All the nodes, that's not I coming. Now, and you perform this integration with respect to all the fj. Technically, you cannot, right? And the theory here is that if you have a lot of random variable coming in, and you do the large linear combination of it, what is the distribution of this? Central limit theorem. What do you say? Got to be Gaussian, right? It doesn't matter what distribution you have, it could be exponential, anything, a lot of them. As far as you do the linear combination, you add them up, you average them out, it got to be Gaussian. So they treat this message, something the combination here is Gaussian. So all these things coming up, it doesn't matter the media it is. Product of this, as far as it becomes large, this product look like Gaussian distribution. Right? In random variable, if you do addition, random variable in the BDF is the product. So we have this, we treat this as Gaussian. We have this first portion Gaussian, this one Gaussian, and guess what? If the two BDF of Gaussian, two Gaussian BDF multiplied together, you have another Gaussian BDF. You take the integration of it, you still have a Gaussian BDF. All right, so the theory is that it doesn't matter how complicated your stuff is, in the end of the day, as far as the system is large, you have a BDF distribution. sorry, you have the Gaussian distribution. So the message here become Gaussian. That's the theory. Now, if you look at the, we can compute all the parameters here and then make the message come in from the factor norm here back into the variable norm Gaussian. And now at the variable norm, once we combine all the messages coming in, again we have a product of them, all the messages, product of the Gaussian multiply Gaussian multiply Gaussian, we have Gaussian. That's the key point. So you can think of this portion is just Gaussian, right? You have the prior information. Then it's possible that you may be able to figure out what should be the message to the other direction. Okay, the blue one. So you combine all the red one, the message coming in the factor norm with your prior information, the green one, figure out what should be the message back. So the theorem here is everything is Gaussian. That's it, right? So the AMD algorithm is exploit the similarity between the messages. You think that there's a message from one side to the other one, and then from the other one to the other side. So the AMD algorithm employs Taylor series approximations of their difference, so that when you do Taylor approximations, there's some error, some term, third order, the second order term, the third order term, so on. So you keep only the first term, the first derivative. All right. So back to the day, because I'm teaching the course in mathematics for engineers. So I know that I cover the Taylor series approximation. Probably you know that there's some term like the first derivative, second derivative. The more terms you have, the more accurate approximation you have, right? So this algorithm, you only keep the linear term. You just ignore the rest. And that would, you have to simplify the calculation for the message. So instead of you have 2 to the m, 2mn message, why 2mn? Because from here, each node will generate n message. And then from the other side, you generate the n message. So the whole network would have 2m times n messages. That's a lot. We don't want that type of many messages. So because of the approximation, you might be able to reduce the number of messages because they are similar. So we keep it only n messages from one side to another, and then n messages from the other back to the factor norms. So that's coming up with the idea of the algorithm, and we generate some estimation for x, and then we calculate the variance. We have some things we call the denoiser, and the other factors here is because the on charger residual the correction to n. This we call the residual. So that's the theory behind the AMP, and I think 10 years ago it was one of the most beautiful things from the mathematics side. Trust me, it's one of the most beautiful algorithms out there. If you're curious about signal processing, it's so beautiful that I will show you the result, how quick how the algorithm performs, right? All right, so but there's something that I bring it up, and I hope I share with you guys. So we got some notation here, something eta here, we call the denoiser, and then the derivative, the denoiser. It's not that easy for to understand right away, and frankly, it took me like 2 years to understand. It's still I'm not understanding it entirely, but we need to figure it out, and if we need to apply and use it, why not? All right, so the denoiser is something like this. So when I had information for z, some estimation of x, and we had the noise, we call the tau z, the noise. So basically, we had a model we call the Gaussian model. We had z equal to x plus some Gaussian norms. So now, if I have z and observe z, I want to estimate x. So this is a very basic estimation problem in Gaussian channel. Okay. You observe some noisy version of X and you want to recover X. Right? You had an image, noise S on, how do you remove the noise out? That's why they come from the term called denoiser. Technically try to remove the noise. So we can look at this from the Bayesian perspective, right? If the noise is Gaussian, very easy, we can find what's the distribution for X. All right, so the image of X, even that your current image, then the noisy image Z. So we use Bayesian theorem, look at back, and try to cover it. So the beauty of AMP algorithm is that you had a couple and system, AX plus noise, which is coupled, and we want to decouple it. We want to make it into individual problems, smaller problem that can be solved easily. And a lot of automation problem is like that. You had something like 1,000 variables, want to optimize at the same time, you cannot do it. Let's make it into 1,000 smaller problems and do it individually. Right? That's that idea. So there's two types of denoiser here. One is the MMSE denoiser, and once you see the term MMSE, it means that you take the posterior expectation. If you see the term we call it the map denoiser, which you can try to find the maximum value of the posterior distribution, we perform the proximal operator. Right, so it's a lot of technical math here. I put it there. Again, also for me for reference in the future, I just look at my note again, and I don't need to refer to other papers. But some special case, right? So if you have axial Gaussian, for example, Z is your observation, Gaussian noise. When you observe Z, you can have axial also Gaussian. Prior is Gaussian, noise Gaussian, posterior is Gaussian. Right. So if it's Gaussian, we can figure out the mean and then the variance. And by the way, for Gaussian distribution, two parameters you care about. It's just the mean and the variance. Okay. Exponential distribution, you only care about the decaying factor. Right. So some distribution, you only know the parameters to describe the distribution, how it looks like. Right? Gaussian mean and variance is enough to tell where it looks like, how spreading it is. Anyway, so that's the theory. And by the way, there's something we call the divergence. Again, this term. We have to calculate the error in the estimation using the denoiser, and it involves some derivative here. And there's a name we call the divergence. And again, it's another term that took me a while to really understand it. So it's just that the denoiser, you take the derivative of it, right? And then if you have separable denoiser, you can take the sum of individual derivatives. And something really weird that if you have the denoiser is MMSE. So if you take the posterior mean is your denoiser, then the derivative is the variance. Okay, the derivative of the expectation is the variance. Very strange. Right? So that thing is become the variance. Now for the lasso thing, and just remind you, the lasso algorithm, we don't have the thresholding algorithm. So the function look something, I don't have the marker here, but this is you have it and it go like that. So it go like this, pattern like that, right? So that's it, the thresholding algorithm. If you take the derivative bit, then some portion of it become 1 because it is the function that's had a slope of 1. Anything in between had a slope of 0. So that's allow you to calculate the gradient. And the key thing of this algorithm is we call it the on-Sarger's corrected residual. And this term actually comes from theoretical physics. Everything connected together. And a lot of guys from theoretical physics jumping into this topic. They are relevant to statistics and things. So the idea is that we introduce something, they introduce something called uncharted corrected procedural. It allows you to decouple the system into parallel system. And that's the key difference compared to E-star. Right, so let me compare to you guys to see this. So this is the ANP algorithm. The E-star, if you ignore everything, if you ignore the residual here, the uncharted correction, ignore this, you ignore this thing, you ignore this thing, you have set this, and this. That is the E-star algorithm. Right, so the key point is the uncharted corrected residual. All right, so let's see. In terms of implementation, be careful. The algorithm, a lot of times it will diverge. Right, so let me finish. Okay, so the key point is that it can diverge easily. It's not like very stable, very consistent like E-star. So be very careful when you implement this algorithm. This is because the residual here, it can blow up. Okay? If you have kind of a state machine that you keep add on the stuff, if you are not careful, this can blow up. Okay? It's like the feedback loop. If you keep add on, unless the thing you add on is getting smaller to zero, if you get otherwise, it just blow up the system with the feedback loop. All right. Now this is a demonstration to you guys how cool it is. All right. So let's see. One example here. I do signal recovery. So I want to recover X. Let's assume that first is X is have about 80% sparsity. So only 20% of it is non-zero, 80% are zero. Right, so I perform, let's say I run E-star, and then I run A and B with ablation, which is lasso, and I run A and B with Bernoulli Gaussian, meaning that B of X, the prior information is Bernoulli Gaussian. So Bernoulli Gaussian means that it's a lot of zero. If it's not zero, then it follows a Gaussian distribution. All right, so if you look at the top, E-star is converged, A and B converge, the blue one, and it's converge much better, faster, better estimation. If we do A and B with the sum product, the expectation, what's the expectation? It's even converged so faster, so much faster. It's dropped like this. Okay. Another example here with 5% of the prior information of X is non-zero, 95% sparsity. So if I run the E-star, it looks something like this. You take about, I would say about 60, 80 iterations to converge. Now, if you look at A and B, it runs like about 40, 30 something here. But if you apply A and B with Bernoulli Gaussian, it's not something like that. Okay, it's not like it did only about less than 10 iterations. So this is one example. Some example that can run like this stock can run 1,000 iterations. It go and then it's go very slowly converge. A and B is just not like it. And in terms of computation, it's just A and B, just much better.
Error is also less.
Yeah. Yeah, the error is also less. The key idea is because of here, the prior information is the Bernoulli Gaussian, and the A and B, I get the information is the Bernoulli Gaussian inside. But with the A and B, if I just think it's as a lasso problem, I mean that I ignore the Bernoulli Gaussian, I just think it to be Laplacian. So there's a mismatch in the distribution. That's why it's not as good. But if the prior information is fitting correctly, it's much better. So this is a stunning result from the whole community 10 years ago. All right, so I think that I got to complete the talk today. I mean, I had a lot of slides. I just finished half of it. I know this. That's too much here in terms of math. If we talk about this, it could take a few hours. to go over the details. So I go quickly here. The next one is we call the generalized AMP. We want to use the AMP framework to solve the logistic regression problem. Okay, you know that logistic is that you take the side, either that your value is plus or minus 1. This is the classification problem in machine learning. And we want to recover X within the features, the weights for the feature. All right, so the general IMP can solve these cases. It's more general than the AMP. AMP is just for logistic, for rich regression and lasso. GAM allows you to solve the logistic regression and many more.
How much time do we need?
Pardon?
How much more time we need?
No, I have finished it. 2 more minutes. I can just go quickly. All right, so those applications not so easy to understand, but the idea is also apply denoiser, input, output denoiser. But in some implementation, if you are curious enough, you do it, be careful. The AMP algorithm is, you can easily diverge. You can easily diverge because of the loopback, the feedback loop, right? And then you had something called bilinear GAN. This is also a very strange problem. That's, if you observe something like AX plus noise and you observe Y. So let's say that problem you have. How do you recover A and X at the same time? Right? This problem we call the deconvolution problem. You have two unknowns and you observe something. How do you figure back the two unknowns? They multiply together. Of course, there are multiple solutions, but from the statistic point of view, if you have some distribution for each of them, then you can figure out the best estimation for each of them, right? And there's the vectors, AMP, and other versions. Okay, I think I skipped to that. My research today is on the second topic. I think I should ask for one more hour to talk about this thing. So the next topic is VB, variation basin. So if you pick up the textbook from Christopher Bishop, anybody know that? Pattern recognition and machine learning. It's the Bible for machine learning, right? So if you look at that, there's a whole chapter talk about approximate inference and they talk about variation basin. It's a well-known topic. It's just the idea of you try to figure out the best approximation for your posterior distribution. And so like 20 years ago, this idea will apply for the latent Dirichlet allocation. The LDA, that's the one that allows you to do classification of text. Right, so that was also a famous problem using this framework. So my research these days, I use this thing to solve my problem. I know this again is involved a lot of mathematics. I had the whole paper, try to connect VB and AMP and then each star. We look at the compare them, and somehow the VB looks more stable than the AMP. That's from the empirical result. It converts more stable. I don't know why. So that is the theoretical thing that I had to look at that in the next few years. If you are curious on this, we can talk more. I need some guy really strong in math to prove this for me. I couldn't for now. All right, so some application. We talked about regression before, right? So I want to talk about compressed sensing. This is the case of you try to recover something with less measurement than you need. Let's say that you have some image, right? Something like, let's say a megapixel image, but you don't want to collect a megapixel. Let's say that you collect 10% of it, and then can you recover the original image? This is very important in MRI because it takes a lot of time for you to take the picture from MRI. And if you can take less sample than the image itself, you can save a lot of effort. Okay, the image layer, million pixels, but that you want to collect 100,000 samples only. You save the time by a factor of 10 times, right? So a lot of image actually is very sparse. meaning that a lot of things can be zero. Right? So if you look at Fourier transform this image, you zoom it, take a lot of zero. So imagine 90% of the coefficient becomes zero, and then I do the inverse Fourier transform. I still look at the image very, very simple. Okay. So it is small somehow, and then we can use the all the things we talked today, A and P stuff to recover the image. So here's the sample. That's I use A and P with lasso to recover the image. Okay. Lasso induce sparsity. Rich regression does not induce sparsity. So in terms of recovery, rich regression needs this kind of image, but lasso is closer to the original. So this is one application from Google compression. So I think I finished now. It's almost an hour. All right. Yeah. So it's
Next time. Any questions? Math having thought.
Yeah, I know this topic is a lot of math. I don't have many demonstration to you for this. Yes.
You mentioned that variational Bayesian is better than A and B, but you can't prove.
Yeah.
But in the starting of the talk, you mentioned like when it becomes discrete problem, when the feature is discrete, then it becomes more difficult. So is it true for discrete space also? Or
Yeah. Yes. Yes. So now the discrete one is the key point. That if you look at the when you try to find a posterior distribution. Okay, so get back to this equation. I think this one is called the discrete. It's very cool things. So technically, if you have a decoupled system, you have this discrete, and you have the observation, so you can calculate the posterior distribution of x easily. If just one plus something, you can recover it back. So that's why we had to do the decoupling. And both VB and A and B, you can decouple the mixing system into individual parallel system. All right, that's the key point. You mix together, but then you do something to untie it into you untie and parallels the problem into individual problem and solve it in parallel.
Right. What makes it difficult to like if it is in discrete domain? What makes it difficult to
Compute the posterior distribution or what? Or just the algorithm itself?
So is it the integration in
Yeah.
that is difficult?
Yes. The integration here, this one is difficult. This one is difficult. All right. So this is actually discrete, of course, is difficult. Let's say actually exponential or anything else is set Gaussian. So we always model the noise to be Gaussian. This is Gaussian. Only when you have Gaussian, multiply Gaussian, you have Gaussian. And integration of Gaussian, you get back to Gaussian. And then you have the division. So Gaussian divided Gaussian, you get back here is also Gaussian.
What if noise is not always
No, Gaussian is different story.
It's not always.
Okay, it's not always true. That's why the GAM algorithm works here. The GAM algorithm is very general. You can generalize it. The noise, let's say noise can be logistic. Any distribution is fine. The overall picture, but some of them we cannot calculate in closed form, even that you decouple the problem. But because the noise is not Gaussian, you may not to derive the posterior distribution in closed form. So,
Any other question?
all right. So if no questions, we can finish. Thank you for coming. I know this topic is very technical and it's very tough. And I'm still learning it. I think it's just cool because have a lot of application. I'm not the guy who bring the topic from the application side. I just go straight to the math. But in terms of biology, image signal processing, recovery, it has a ton of applications. Think about you have a big image, but then somehow you just only take a few samples of it, and then you still recover the whole image. How cool it is, right?
But we do lose the high frequency.
Yeah, of course. You do lose the details. Yeah.
We had once used on H.264 video, we used the lasso and logistic regression.
Yeah,
And sometimes one worked better than other.
that's true.
We could not, know the reason, but used it as a black box. Lasso did not outperform logistic regression every time.
That's true.
Sometimes it did, sometimes.
It just depends on the original image that it can be small in some domain, not to be small in some domain. Then you can apply it. Thank you.